And like I said, I'll try to get the projects posted as soon as possible. Okay. So let me write something down here before we get going. So this will be signal to noise ratio. You know what? That pin needs to get thrown away. So 6.1.1 signal to noise ratio, passive noise shaping. Okay. So did everybody get a chance to read that section or those sections over the weekend? Yes? Easy? All right. So let's go back to where we were. And what I'm going to do is take the right where we left off. I'm going to write the output signal in terms of the signal transfer function, 1 over 1 plus j omega RC V in plus the noise transfer function, j omega RC, all over 1 plus j omega RC times VQE. And then this extra term here, which is the distortion term. Does anybody recall how we get rid of that in most of the delta sigma modulators? Yeah, use an active integrator, and then that means Vint goes towards 0, right? Minimizes it. So we'll talk about using an active integrator. I'm going to take this term right here, and I'm going to call it VQE of, what did I call it in the book? VQE of F times the noise transfer function. So here's where I cringe, but we'll see what happens. So I want you to sketch here against frequency VQE of F. Okay? And that's VLSB over root 12 times Fs. And this has units of volts per root hertz, the way I've drawn it. Oops, over root 12s. Okay, so with what we did before, we had a 1-bit quantizer. What is VLSB? Yeah, it's VDD in our example, right? Because the output of the comparator goes from 0 to VDD. Any questions? So this is relatively a big amount of quantization noise because of that. Okay, what is the shape of this? It's a high-pass filter, right? It does this. It goes up, and if we keep going, and it goes up and then flattens out at what? What's a high-pass? What does this filter flatten out? Wait, no. What does it flatten out at high frequencies? How are V in and V out related? They're equal, so where's this equal to? 0 dB or 1. No questions, right? So then I look at, okay, what does the shape of the quantization noise look like? Not losing anybody, right? Okay, the shape of the quantization noise would be the product of those two right to this point. Okay, so now I want to calculate, so this represents the noise that's in the output of the noise shaping modulator in this case, right? So I want to calculate the amount of quantization noise in the output of the modulator, but I know for this to work, I have to pass the output through the output's 1 bit. That's not very useful, right? So I got to pass that 1 bit through low-pass digital filter. I fake it in the simulations with a RC circuit, but what I really need is a digital filter. So I'm going to write here that my digital filter has a bandwidth which is B. And so I'm removing all of this quantization noise, and the only thing that's left is the quantization noise down here. Now remember in my example what I showed this was the clipboard, and I was averaging the number of points, and we said that using noise shaping doesn't reduce quantization noise, it simply pushes it to higher frequencies, hence the name, okay? So here I remove the high frequency quantization noise, and what's left is the RMS noise right here in the spectrum. And so next I'm going to calculate this. Any questions? Okay, so I go back. Yes. So that's the thing. You need to have a sampling frequency that's very large relative to your bandwidths of interest. And so that's one of the drawbacks of just using basic noise shaping. Now, of course, if you do bandpass conversion, you can have a output which is a small, I mean, you can get very good sampling ratios because you're digitizing over a small bandwidth at a very high frequency. So if I had a sampling frequency of a gigahertz and my signal frequency here were 10 megahertz, then I'd have 100 to 1 oversampling ratio, okay? If I had a gigahertz and then I had 250 megahertz as my band I want to digitize around for a band pass, then I could go 240 to 260 and I would still have 100 to 1 oversampling ratio because I'm digitizing over that bandwidth, so it's kind of shifting it. So but that's one of the things in your projects. We're going to get around that by using we'll use 1 sigma for summing just like we did before, but we use k delta. So we use multiple feedback paths which are time delayed to jack up the effective sampling rate so we can do effectively larger oversampling ratios for given the sampling frequency. Did anybody follow that? Okay, so what we're going to do now is calculate that noise. So let's do that, and let's see. So we got our noise, RMS noise. How does that keep getting tweaked? RMS noise squared, we'll say, is the summation. We'll do both sided spectrums from 0 to B. So I'm assuming a brick wall filter of the noise transfer function times the VQE of F dF. And if you look at this, is you can see the derivation in figure 613. I'm sorry, equation 613. And let me just pause for a minute because this we can move to the outside because it's not a function of frequency. It's flat, so it's VLSB squared over 12 times F sub S. And then this term here, so the assumption here is that we're staying at low frequencies. So this transfer function is approximately just 1 over, and this is it's just the DC portion. In other words, we're staying away from the 1 over 2 pi RC here that's out here, so that the transfer function is approximately just this. Did I lose anybody there? So if we band limit our filter so we're over in the lower frequencies, then we're not going to have to worry about the pole, so I'm not going to carry it through the integration. Okay, so I write that as then the integral of from 0 to B of just the numerator part, which is 2 pi F times RC squared times DF. And if you plug everything in, you get 2 VLSB squared over 12 FS times 2 pi RC. And then F squared is 1/3 F cubed, evaluated at 0 and B. And you never thought you'd use that freshman calculus. And you plug that in, and of course it becomes 2 VLSB squared over 12 FS times 2 pi RC. I made a mistake, didn't I? Yeah, times 1/3. I was waiting for you to tell me, man. You're probably so used to them. I'm not. It's just him making another mistake. Okay, over the b cubed. Now, if you recall in our filters, we had bandwidths where we had it where this was f sub s over k, and then half of that would have been f sub s over 2k. So I'm going to use that for my b in order to try to get an idea for the quantization noise. So I'm going to put the b equal to f sub s over 2k. Did I lose anybody there? I'm just saying that the filter, I'm taking this as my bandwidth of my filter. Okay, so you could argue, well, wait, over here you have more noise and over here you have less noise. It's just to get something useful, okay? So I'm going to plug that in here, and what I end up getting is VLSB squared over 12 times 2 pi RC squared times FS squared, because the FS and FS cube cancels, over 12k cubed. Looking good? Okay, so just make an observation here. If I increase k, just looking at the equation, what happens to the noise? If I increase k, yeah, it goes down, which means I'm reducing the bandwidth of my filter, which means my comb filter has more delay elements and I'm choking off the noise. The drawback is, of course, the bandwidth is reduced as well. Okay, makes sense? So now what I'm going to do is I'm going to take this and I'm going to plug it into the, yes. I'm going to plug this into my equation for SNR, and then I'm going to try to get an idea for how my SNR changes as I increase K. Okay, so I'll take this. And if you want to follow along, this is on page 209. And I'll write SNR ideal. SNR ideal is equal to 20 log of VP over root 2 divided by V noise. And I'm going to borrow what we had before. What was our V noise RMS before here? I have to take the square root. This is V noise. So would everybody be cool if I note that V noise RMS, if I take the square root of that as VLSB over root 12, this is just my normal noise, and then I use that in the effective bits calculation. So in the effective bits calculation, I got that 6.02n plus 1.76. I want to put it in that same format so I can see how the added averaging affects things. So if I do that, then I can write 6. I'm going to actually, since I want to get through more stuff, I'm going to write 618 directly. 6.02 n plus 1.76 minus 18.06 plus 30 log of k. Question? Why did I do that? 4.4 TS. The value of RC must be at least 4.5 times the sampling period to keep TS and VN from varying too much. If we set, well, wait. So remember this discussion here of the VINT, that's only for passive. So that's for when we use active integrators VINT 0, so it doesn't matter. So if you go back and review, you'll see why I use 4.4 here. But the reason I didn't follow the guideline is that I wanted to make an equation that's useful in the future and then following where the 4.4 came from. So here's the thing, if you have a really large RC, then you're not going to get much variation because you're really filtering it a lot, right? And if you keep your input signal, I should qualify that with saying if you keep your input signals slow, okay? Because if you keep your input signals fast, then it's going to vary a lot anyway. So there's a lot of gray area. Did that make any sense? So let me repeat. So in active integrators, V-int is 0, so that's not an issue. Okay, and I'm trying to make this generic for the generic delta sigma case, okay? If I use slow-moving signals, then I don't have much variation in V-int anyway. Okay, so if we go back and look at these discussions of 510 and 513, yeah, that's just following that. So why did I use 4.4 though? If we set RC equal to 4.4 TS, and I think I did that so that this term here would come out to nearly a whole number. That would be what I guessed. It's not that critical as the bottom line, okay? You don't have to. You can leave it in this form if you want, okay? That would, just looking at it real quick, that's the only thing I can figure is to get roughly a whole number right there. You get this equation. So the whole point here is that if you use noise shaping and you don't use oversampling, you actually get a poorer, because you can use more than a single bit quantizer, you actually get poorer signal to noise ratio. If you do use noise shaping, you got to use a K that's large enough that you actually overcome this 18 here. And I wanted to plot a comparison. So this would be just using simple oversampling. So an ADC going to an averaging filter, not very good. And then here you see what it is. You get 1.5 bits increase in resolution for every, so it's dramatically better than simple oversampling for using first order noise shaping. So if I were to, for example, average 16 points for noise shaping, I would get an increase in resolution of roughly 3.33 bits. Does everybody follow that? Okay, so let me ask just to make sure somebody follows. If I take that passive noise shaping modulator and I say I want to have a effective increase in resolution of roughly 3 bits, so tell me how many, what's K have to be? It's got to be, yeah, roughly 10. And then if I ask what's the effective resolution, it's the 1-bit quantizer, so 1 plus 3. So 4 bits. So if I wanted to get 10 bits, I would have to go back and look at the equation, but I basically have to oversample by 1.5 by 6 times, so 2 to the 6th. Okay, so I think everybody got lost on that one. So let me write it down. So if I go with 30, well, let's ask even something simpler. If I increase my resolution by 1 bit of just a normal data converter, how much does my signal to noise ratio go up? 6 dB, right? Okay, so every increase in 1 bit is 6 dB. If it's 1.5 bits, then my SNR goes up 9 dB. Okay, so if I go over here and I do 30 log of, let's do 8. K is, K is 8, okay? And I ask, all right, what is log of 8? So yeah, log, where's log? There it is. So 0.9, and I look at that, and I say, okay, it's 0.9, so this becomes, let's just write the overall plus, so this becomes roughly 27. Did everybody agree? And so if I put 8 in there and I ask what's the result, how many dB did this go up? 9. So I'm starting out and I've got 9 dB or 1 bit increase in resolution. Let's say that I double the oversampling ratio or I double the number of points. So then I'm at 18.06 plus 30 log of 16, which we can probably all do in our heads, but what does that result in? Here, let's do the math instead of saying we can do it in our heads. So then I go, all right, so I got 16 log 1.2 times 30 equals 36. We'll just round it to 36. So this goes to 36, and then this becomes 18. And so then how much, from doubling our oversampling ratio, how much improvement in signal to noise ratio did we get? 9 dB or 1.5 bits. Have I made it clear that every time I double the oversampling ratio that I get 1.5 bits increase in resolution? So I could do the next, I could do 32 and it would go up to 27, the difference, etc. So is that all clear to everybody? Okay, so if I go back and I look and I say, oh, that's what he's showing right here. The slope here is 9 dB for every doubling of the number of points, or for every octave if you want, or it's 30 dB per every decade. So if I go from 10 to 100, which is 1 decade, I go up by 30 dB. Any questions about that? Okay, so proof's in the pudding. So I want to do this example right here. But before I do that, this is the noise shaping modulator, figure 6.4, its output's 1 bit. So I'm using 16 points. So based upon what I just wrote here, I expect to get how many bits increase in resolution? Wait. Yeah, 3 bits. So my final output should be 4. Now I round up because it'll be slightly more than 4. Okay? So that's what I expect to see. Now, before I show you the simulation, tell me what I'm doing here, just as a sanity check for myself. Yeah, I'm decimating and filtering at the same time. So everybody sees what's the point of these registers? To retime the data so I don't get a race condition. So just make sure that, because there's a 1 here, that it doesn't fly through. Okay, does anybody not see how this equation is implemented at this point with this digital hardware here? Okay, so what I want to do now is I want to go look at the sim and I want to look at each one of these blocks and I want to see how I handled the number of bits and how I converted this to 2's complement and then how I look at the output and all that. So let's look at that. Wait, are there any questions? Because this sim I'm about to show you has a lot of the concepts we've been building up to in the class. So let's go here. And extract here. And we want 611. And I'm going to zoom in on this part right here. You see I've got a VDD of 1 volt. Common mode voltage is half a volt. Then my input's a sine wave with a 900 millivolt peak amplitude down to 100 millivolts, swinging around the common mode voltage. Now I'm not doing this to make it unnecessarily hard, because it would be much easier if I used ground as the common mode voltage and plus and minus supplies. But basically for the last 20 years nobody's been doing design like that, so I'd rather you do it like is actually done. I mean, I'm not going to say nobody, it's just not as common with all these, you know, big systems and single batteries. Okay, so there's my clock. I'm running at 100 megahertz. There's my noise shaping modulator. It's passive. I got 10K feedback resistors. There's my sigma. Because I'm inverting my output, I'm taking the difference between my output and my input, the difference in the currents. Tell me how I could get rid of not Yuang Shaman, but somebody else, how could I get rid of this inverter? And what would be the drawback? I want to make sure what I feed back is inverted so it subtracts with the input. So how would I get rid of the inverter? Just swap these two inputs. So put the minus over here and the plus over here. The big difference is then I'm inverting it. Since I'm going through here and I'm going to the minus terminal, I'm inverting the signal so my output would have a 180-degree phase shift. But if I was really worried about hardware, I could get rid of the inverter. Generally, they don't in hardware because they want this to be really isolated and tied to very precise reference voltages. Okay. There any questions about this circuit? Does everybody understand if I flip the plus and minus on the comparator that I would invert the signal and not need this, but then when I did the digital filtering, the output would be inverted? We can, well, we don't have enough time, but if you want to, you can do it on your own. Okay, no questions on this circuit. So doing a data conversion, very simple. Then I look at the output here, and I go to 1 plus z to the minus 1. But wait a sec, the output's 1 bit. So when I go in here, what do you think I'm going to see? Well, let's see. If I have 1 bit coming in, it gets clocked in. Wait a sec, something's not right here. Bit A, bit 0. Oh, yeah, okay. I was going to say, we're missing a direct feed-through path, but if I highlight this, you see it goes all the way through. Then an adder bit. Okay, so what's up with this? How does this work? If I have a whole bunch of zeros coming in, what are my outputs here? 0, 0. If I have a whole bunch of ones coming in, what are my outputs? My output's 1, 1, right? So wait, that has me concerned, all right? So let's keep that in mind. Okay, does everybody see that? That's outputting 0, 0, and 1, 1. Okay, why is that? I'm saying that, and I'm assuming everybody knows. What's the concern? Well, it's not in 2's complement, right? So if I have 1, 0, 1, 0, 1, 0, what do I get constantly out of here? If I have 1, 0, 1, 0, 1, 0, what is S1 all the time and what is S0? What's 1 and 0 added together? 1, so sum's 1. What's the carry out? There's no carry, right? There's no overflow, it's 0. So I constantly have, this is 0 and this is 1. If I have 1, 0, 1, 0, 1, 0. If I have constant 1s, then this is constantly 1 and 1. Or I'm sorry, 1 and 0. And if I have 0, 0, then they're both zeros. So I need to keep that in mind. So I'll go to my next stage. There's my 2-bit register. Nothing interesting going on there. And I look at what's happening here, and I'm like, doesn't use 2's complement. Well, wait, how does that work? Well, it works fine. How does that work? Yeah, we can talk about that later. All right. So then when I get to the very end, what's the format of my circuit? Multiply by 2, can overflow, hit run. Still binary offsets. I don't need to offset binary. I don't need to convert it. Let's look and see if we actually do data conversion. What's the point? So this is my digital filter. Maybe we did cover this, and I don't remember covering it. It's in the book. What's the point of the 500 ohms and 0.1 nano? Yeah, it's kind of filtered to show that it's sine wave-like. You really don't need that. It's just for the human eye. It's nice to go, oh yeah, that's a sine wave, and I could filter it more. You can see here. Okay, so does everybody see the blue is the data converted digital representation of the input? Why isn't it at the full amplitude? Maybe the filter's influencing it. I don't remember. You could look in the book. I'm sure I put a comment on it. And also there's quantization noise. It's only a 4-bit ADC, so there's quantization noise in the output. How would I how could I do this without decimating? We'll do it later, but then there's probably a sim in this file, but I just use a filter, right? 1 minus z to the minus 16 over 1 plus z to the minus 1, and just connect it directly without doing the decimation. Okay, so this is decimating and filtering all together just to prove it, and I can do the same thing but without decimating and go directly into the DAC. Okay, so does everybody, we're over time. Does everybody follow what we've done? How we're doing analog to digital conversion using signal processing. There's not one analog op-amper in that circuit. Okay, so it's pretty powerful stuff. Have a good day. Good luck on your test on Wednesday, and I'll see you on Monday.